Thank you, Dr. Aziz, for the nice introduction. And good morning, everyone, and welcome to my PhD defense. So in this presentation, I'll be talking about my PhD works on cryogenic computing, and I'll also be talking about how we have utilized different superconducting and topological devices to redesign different components of the computing system. So here's the outline of my presentation. I'll start with a brief motivation behind my research. I'll talk about why we need cryogenic computing. After that, I will talk about the existing cryogenic technologies and their challenges. And then I will move to my works on cryogenic computing. And for the ease of discussion, I have divided my presentation into two portions. In the first part, I'll talk about my works using superconducting technologies. And in the second part, I'll talk about my works using topological devices. Finally, I will conclude my talk by summarizing the contributions, and I'll also share a few possible future extensions of my PhD research. So let's start with the motivation behind my research. But before that, I'll briefly talk about what is cryogenic. So cryogenic refers to a low temperature environment. Theoretically, any temperature below 100 Kelvin is considered as cryogenic temperature. But there are some specific temperature ranges which are mostly used for different applications. For example, we have this 77 Kelvin temperature, which can be achieved by using liquid nitrogen, and they are mostly used for cryogenic CMOS circuits and systems. Then we have this liquid helium temperature, which is 4.2 Kelvin. They are mostly used for superconducting electronics. And then we have this millikelvin temperature range, which has recently become very popular because of the emergence of quantum computing applications. We place the qubits at this millikelvin temperature. But the question is why we need cryogenic computing by using this huge cooling cost. So there are two major reasons for that. The first one is when you go to cryogenic environment, we observe improvement in different performance metrics. For example, if we look at this figure here, when you go to liquid helium or 4.2 Kelvin temperature, with these superconducting circuits, we actually get at least 1,000 times improvement in computing speed compared to the room temperature technologies. That too with 100 times lower energy requirement. And as you can see, this is a significant improvement compared to any other room temperature technologies. And that can be useful for developing a high performance computing system to handle the modern data intensive applications.
Can I ask
Sure.
what do you mean by energy improvement? Because you need energy to bring the temperature down.
Yes, but I'll show in one of the next slides. Even with cooling cost considered, people have reported that with superconducting electronics, we can get at close to 100 times better energy efficiency compared to the 7 nanometer CMOS technology, which is one of the most advanced versions.
So that number that you showed includes.
Includes the cooling cost. Yeah.
So are you going to address the cost of helium being so much more expensive than nitrogen, or are you assuming a closed system?
No. At liquid helium, we need like at least 200 times more cooling cost compared to liquid nitrogen.
Yeah.
So that's also well known. Yeah.
So, but somewhere you're going to comment on that, or?
Yes, somewhere when we
Okay.
talk about the superconducting electronics, I'll
Right.
talk about that later.
Thank you.
Yeah. So, and the second reason for going to cryogenic environment is there are some exciting fields where we need actually cryogenic circuits. And these are the three very exciting fields which can benefit from a suitable cryogenic computing system. So I'll talk about this one by one. Let's start with the most exciting one, which is quantum computing. So quantum computers are nowadays very hot topic because they can solve the limitations of classical conventional computers that we have. So with the classical computers, we cannot solve many important problems, not at least in a realistic time frame. For example, if we want to simulate large scale molecules for drug discovery or other applications, we need a ridiculously high amount of time with classical computers. And same things happen if we want to perform large scale optimization problems with the classical computers. But if we have a quantum computer with a reasonable number of qubits, we can solve these problems, same problems in a few minutes. And that's how we can bring revolutions in multiple important fields with quantum computers. But one of the major challenges for the existing quantum computers is their scalability, which is increasing the number of qubits. And the reason behind that is the arrangement of different components in the existing architecture. So in a quantum computer, we have three major components. The first one is qubits, which are responsible for mostly for all the computing tasks. There we use the quantum phenomena like superposition, entanglement, and so on. And these qubits are extremely sensitive to external noise. That's why to protect them from thermal and other external noise, we put them at extremely low temperature, which is in the range of tens of millikelvin temperature. But to control this and read out these qubit states, we need a cryogenic controller, classical controller and a classical memory system, which are currently placed at room temperature. Now you can easily imagine if you have some components at room temperature and qubits at millikelvin temperature, we'll need a huge amount of wires and interconnects to make this classical quantum interface. And it has been reported that to control a quantum computer with only 53 qubits, it was reported in 2021. So they needed 200 coaxial cables, 45 microwave circulators, and a rack full of electronic circuits. And again, if you want to scale this quantum computer with thousands or millions of qubits, which is the ultimate dream, these numbers will increase exponentially, and that will limit the scalability of quantum computers. And also there will be another challenge, which is these wires and interconnects will have a large temperature difference between this room temperature and millikelvin components, and that will cause heat dissipation from room temperature to this millikelvin qubits. And again, if you try to scale this architecture to thousands or millions of qubits, the resultant heat dissipation will be sufficient enough to destroy the qubit states. That's why it's well known this existing architecture where we have some components at room temperature and the qubits at millikelvin temperature might work fine for hundreds of qubits, but it will never be able to scale to thousands or millions of qubits. But to achieve complete supremacy over classical computer, we actually need thousands or millions of qubits. For example, if you want to run Shor's algorithm of prime factorization on a 1000-bit number, we will need more than 4,000 ideal qubits. And if you again consider additional number of qubits required for performing the quantum error correction in these qubits, the total number of qubits will be close to millions. And with the existing architectures, we cannot go to that many qubits. That's why the goal is to develop a cryogenic controller and a cryogenic memory system so that we can place them very close to the qubits. In that way, we'll be able to reduce the amount of wires and interconnects required to make this classical quantum interface. And also, if we go to this 4 Kelvin temperature, we will be able to use superconducting wires and interconnects, which are lossless because of their zero resistance behavior. So that will also help us to solve that heat dissipation issue that we have here. So again, if you have a suitable cryogenic computing system, we'll be able to scale these quantum computing systems up to thousands or millions of qubits, which is the ultimate dream. The second field that can benefit from cryogenic computing is the high performance computing. So for high performance computing, one of the major issues is their high energy consumption. And the reason behind that is the exponential increase in the amount of data. As you know, and as you can see in the right figure, the amount of data that we create is increasing exponentially every year. And the reason behind that is also well known. We are now using ChatGPT and other AI tools. We are using social media and interconnected mobile devices through which we generate a huge amount of data every second now. And that's why you see the data centers will experience the highest amount of increase in the energy consumption in the next few years. And that will be extremely difficult for us to handle this high energy consumption. And also,
it's the comment, your references are 2018 and 2021.
Yes, this figure.
My guess is, because of what you said, ChatGPT and the like, that it's actually worse.
Yes, but this was, you see, this was projected up to 2005,
Yeah,
but it will obviously
that's
change.
my point. Yeah, so it was projected from before
Yes, exactly.
the emergence of.
Yeah, I think now the scenario will be much worse. Yeah, and also with the existing CMOS technology, we are facing several challenges because we have almost reached the fundamental limit of scaling, and we cannot do too much about the further improvement of their performance. And that's why, again, it was projected in 2022 that none of the existing conventional supercomputers will be able to achieve the DOE's exascale goal, which is shown by the pink diamond here. So as you can see, some of the conventional supercomputers can actually achieve the performance shown by the red circles here, but they need much higher power consumption than the budget. But the scenario is different for superconducting technologies, which are shown by these blue circles here. You can see they can achieve the target performance even with much lower power consumption than the budget. And the reason behind that is the extreme energy efficiency of superconducting devices and circuits. And as you can see in this figure, superconducting electronics outperforms the CMOS technology by a significant margin in terms of both power consumption and switching delays. And finally, cryogenic computing can also be a natural fit for space electronics because, as you can see in deep space, we have this cryogenic environment for free. So if we have a suitable cryogenic computing system, we'll be able to use that for the exploration of deep space, and we'll be able to take advantage of that readily available cryogenic environment there. So we'll not need any additional cooling cost for that applications here. So now I'll talk about the existing cryogenic technologies and their challenges. Because of this immense prospect of cryogenic computing, people actually explored almost all the different technologies for cryogenic applications, which include the cryogenic characterization of room temperature non-superconducting technologies. Then we have these superconducting technologies which are made for cryogenic environment. And people also explored the hybrid approach, where they try to combine the advantages of these non-superconducting and superconducting technologies. So let's first talk about the non-superconducting technologies, which are most familiar to us. So when we characterize these non-superconducting technologies at cryogenic environment, we observe improvement in different performance metrics because at cryogenic environment, the mobility of semiconductor devices increases. So we have better speed at cryogenic environment. Also, the threshold voltage decreases, which gives us a better power efficiency. And also, we observe improvement in the sub-threshold slope.
That's not true. Threshold voltage increases for MOSFETs at cold. Yeah, actually, voltage overhead problem is a real problem at cryogenic CMOS.
Yeah, but we also observe that's true, but we also have sharper turn on, right? The sub-threshold slope becomes
Sub-threshold slope
Yeah,
is steeper.
and yes, and we can use actually lower VDD for that, because we
But-
can reach the on current.
But VT.
Yes,
threshold
threshold voltage
increases.
increases, but because of the sharper turn on, we can actually use lower VDD and we can reach the on current mass faster. So in that, from that, we get better power efficiency and energy efficiency from that. So combinedly, we have better mobility and better sub-threshold slope. So we have better energy efficiency at cryogenic environment. And this was reported in all the experimental demonstration for like cryogenic characterization of CMOS technologies. But the challenge is they are still not compatible with the requirement of cryogenic environment. So when you go to cryogenic environment, we need to use a cooling refrigerator. And for every temperature ranges, we have a certain upper power limit that we can use. Otherwise, the temperature will increase beyond that cryogenic environment. For example, if we operate at 10 Kelvin temperature, we have a power limit of 100 milliwatt. And within this power budget, because of the high power consumption of non-superconducting circuits, their scalability will be limited. And they will end up being the eventual bottleneck for the target applications. For example, if we consider the quantum computing applications, and if we use CMOS technology to develop a cryogenic controller, the size of the controller will be again limited because of this power budget. And that will impose some limitations on the number of qubits we will be able to control with that limited size controller. So we will have some limitation in the target applications with that. And also the speed of non-superconducting technologies, again, are not compatible with superconducting devices and also the quantum quantum computer architecture that we have, because we use superconducting qubits there. So we have mismatch in terms of speed there as well. On the other hand, for superconducting technologies, the power consumption and speed are not concerned because they are extremely energy efficient, as I mentioned. And as I already mentioned, it was reported that even with cooling cost considered, with Josephson junction-based superconducting circuits, we can get 80 times better energy efficiency compared to the 7 nanometer CMOS technology, which is one of the most scaled version of CMOS technology. But they have their own challenges. Again, because of superconducting nature, we need inductors and inductive coupling in all the superconducting circuits. So when you have inductors in circuits, they try to communicate with each other. And when you put different circuit blocks on a single chip, again, inductors from different circuit blocks try to communicate with each other. So to avoid that mutual coupling, we need to maintain a gap between each of these circuit blocks that hamper this integration density for superconducting circuits. And we have very poor scalability from superconducting circuits. And that is a major challenge there. Also, because of the superconducting nature, we need to use current bias in their circuits. So when you have current control logic circuits, we are limited to single fan out issue, because we cannot drive multiple inputs in the next stage with an output current. Otherwise, the current will be divided and the next stage logic gates will not work properly. So we are either limited to single fan out issue, or we need to use additional circuitry called current splitter circuits in between to achieve higher fan out. And these current splitter circuits, again, have multiple buffers in it. So that's why they have significant negative impact on the area efficiency and energy efficiency of the whole processing system.
When you talk about superconductors, you're talking about conventional superconductors or Because they're high TC.
These are low TC superconductors, type 1
So
superconductors.
does it make a difference if you have a high TC superconductor?
Yeah, in high TC superconductors, we are actually can use them at room temperature in environment, right? But the difference is that like for high TC superconductors, we have different like complex alloys. We don't have any metals actually for high TC superconductors. They are difficult to control, and also we need to sacrifice some properties. Like in type 1 superconductors, they cannot be penetrated with magnetic field. But when you have high TC superconductors, these complex alloys, they can be penetrated by external magnetic field. Again, we have to sacrifice some performance metrics there. But by superconducting technology in the whole presentation, I'm referring to the type 1 superconductors. Yeah, which needs like at least liquid helium temperature for their operation. And then to combine the advantages of the superconducting and non-superconducting technologies, people also try to design this hybrid system where it was mostly explored for memory applications, where they use the CMOS memories for storing the data to get high scalability and high storage capacity. And they used Josephson junction-based superconducting circuits to design the access and peripheral circuitry to access these memory cells so that we can get high speed and high energy efficiency from those superconducting circuits. But the challenge is here, we need a suitable interface circuit to connect these two different technologies. And these two different technologies operate at two different voltage ranges. So we need an amplifier as an interface circuit here, which will convert the millivolt level voltages from the superconducting access circuits to the volt level voltages for the CMOS memories. And people have actually tried to design this amplifier with different technologies like semiconducting, superconducting, and also hybrid technologies. But the common challenge is here is that when you use this amplifier, they take away some of the advantages of combining these two technologies, and we don't get the expected energy efficiency and expected speed from this hybrid system. So that's one of the major challenges for this hybrid system. So now that we know about the existing challenges of cryogenic computing, I'll now talk about my works on cryogenic computing, where we tried to solve some of these challenges. But before that, I will try to give you a high-level overview of my PhD research. So to solve these existing challenges of cryogenic computing, we utilize two different technologies. The first one is superconducting technologies, where we use these two unique devices called ferroelectric squid and heater fraction to design different components of the computing system, which includes logic, memory, and in-memory computing systems. And we also use this quantum anomalous Hall effect phenomena observed in topological devices, again, to design memory and in-memory computing systems for cryogenic applications. And I'll try to give you an overview of my contributions. So I have mostly worked on two major avenues. The first one is device modeling, where I have mostly focused on developing compact models for these devices, because when you try to use circuit simulators like Cadence and Spice, you either need PDKs from external foundries or you need Verilog-based compact models. But for most of these emerging technologies, we don't have PDKs from foundries. So we had to develop our own Verilog-based compact model, and I have developed several compact models for different cryogenic devices, which allowed me to explore their circuit and system level applications using these existing simulation tools. Then I also have worked on circuit design, where, for example, I have designed different memory systems for cryogenic applications, where our goal was to develop a scalable and a compatible memory system for this cryogenic environment. I also have designed logic circuits. For example, I have designed this very first voltage controlled superconducting logic family, which can solve the single fan out and limited cascadability issues that I've discussed for the existing current control logic circuits. I also have designed a reconfigurable logic circuit where you can use the same circuit to perform different logic operations. And you see here, we only need one device to perform up to 3 input logic operations. So that will give us better area efficiency, and we will also have better hardware security from this because of this reconfigurable nature of this logic circuit. Finally, I have extended many of my works on memory systems to perform in-memory computing tasks. Here, we have tried to modify the memory system in a way so that we can use the same memory array for memory operations, as well as to perform different computing tasks like Boolean logic, matrix vector multiplication, and so on. And here our goal was to achieve higher energy efficiency with negligible overhead compared to the von Neumann architecture. And as I will explain, that better energy efficiency can also help us to reduce the cooling cost for cryogenic environment. Now I'll move to my works on cryogenic computing. And as I mentioned, I have divided the presentation into two parts. So I'll start with my works using superconducting technologies. And as I mentioned, I will have used these two unique devices, ferroelectric squid and heater fraction, to design different components of cryogenic computing system. And I will talk about this one by one. But before that, I will briefly introduce these two technologies, ferroelectric squid and heater fraction. So this is the device structure of a ferroelectric squid. This is sort of a hybrid device where we have this non-superconducting ferroelectric material, and on top of that we have this superconducting device called squid. So, and squid is nothing but a parallel combination of two Josephson junction, and Josephson junction is the building block of any superconducting circuits that we have. So we know for ferroelectric material we have these two different polarization states, and they are mostly used for room temperature memories. Here we can apply a suitable voltage, either positive or negative, to switch between these polarization states. But when you fabricate this superconducting device on top of a ferroelectric material, the polarization states of the ferroelectric material actually change the interface charge density in the interface of this ferroelectric and the superconducting device. And as a result, as you can see, we get two different critical temperature levels for the superconducting device. And for negative polarization, we get a higher critical temperature, and positive polarization, you get lower critical temperature. And critical temperature is that temperature below which a material behaves as a superconductor or zero resistance. And above that temperature, the material behaves as a normal metal or some non-zero finite resistance here. And we see this effect in the IV characteristics of the superconducting device. And as you can see, the two polarization states of the ferroelectric material leads to two different critical current levels. That means we have two different switching thresholds. So this critical current actually determines the switching from superconducting state to the resistive state for any superconducting device. And as you can see here, we have two different critical temperature levels, critical current levels for the two polarization states here. So this ferroelectric squid device here gives us non-volatile behavior from the ferroelectric material, which is good for memory applications. And they are, as I mentioned, they are already used for room temperature memories. And also here, as I mentioned, we can apply suitable voltage to tune this polarization state of the ferroelectric, which will eventually control the switching of the superconducting device. So we have some indirect control, voltage control over the superconducting device here, which we can use to design voltage control logic circuits. And also, we are also using the superconducting portion in the device, which will give us high speed and high energy efficiency, which are the typical advantages of any superconducting device. So we first developed a Verilog-based compact model for this device. So to model the ferroelectric behavior, we use this traditional Tracer's equation, and we validated our model with the experimental data at cryogenic environment for a lead zirconium titanate ferroelectric. And this figure here shows the validation of our model. And then we phenomenologically implemented the effect of polarization on the critical temperature of the superconducting device, which was again validated with experimental data. And then we use this BCS theory to calculate the superconducting energy gap for these two critical temperature levels that we get for two polarization states. So these two blocks actually give us the effect of polarization of the ferroelectric material on the superconducting energy gap of the superconducting device here. And finally, we can use this AB theory to calculate the critical current level for two polarization states. And then we use the famous RCHJ model for superconducting devices to calculate these IV characteristics for this squid portion that we have here. So this figure here shows the IV characteristics, and both these characteristics of the ferroelectric and the squid were again validated with the experimental data available in literature. Then we use this another superconducting device called heater fraction, and for this we actually collaborated with a group from NIST. They fabricated this device and shared a lot of experimental data with us. We used that data and we developed a lookup table based model to explore their circuit level applications. So in this device, we have two different superconducting nanowires. One forms the gate and another forms the channel. And initially, both this gate and channel remain superconducting, and they are separated by a dielectric material in between. Now, when you apply suitable current to this gate and channel, the gate becomes resistive faster because of this narrow region in the middle here in the gate. And when it becomes resistive, it starts generating thermal phonons. And these thermal phonons are carried to the channel by this dielectric material. Now, if we keep increasing the gate current, that will keep generating more and more thermal phonons, which will be carried to the channel, and that will increase the temperature of the channel material here. And as you can see, with the increase of gate current, the critical current of the channel actually decreases. Now, since we have a constant current to the channel, after crossing a threshold, that constant applied current will be greater than this critical current at some point, and then the channel will switch to the resistive state. So we have here gate current control switching of the channel, like the CMOS transistor, which you can use as a switch in different circuit level applications.
The green is the gate.
The green is the channel.
The
And-
green is the channel.
Yeah, and this rectangle region, that half rectangle region that you see in that is the gauge. And because of this narrow choke region here, they call this choke, the gate becomes resistive faster. Although they are made of same material, they become faster with lower amount of gate current.
So your models here, they're more physics-based or compact?
The heater pattern model was lookup table based model because
Okay.
the physics of this device is not yet well developed. So we use the experimental data that we got from NIST. We got a lot of data for different device dimensions and also different biasing conditions. So we use those data to develop a lookup table based model, which we used for circuit simulator. And we also developed a machine learning based model with that experimental data in our group, but we didn't use that for circuit level simulations.
But the squid, is that the same physics-based model you showed there, or did you have a more compact model?
The ferroelectric squid metal, we use those physics to develop a compact model.
Okay.
Because you see the equations are actually compact and we could implement them in Verilog. So we developed a Verilog-based compact model for the AT squid device using those physics. Yeah.
Is that channel width of 4 microns, is that gonna be a problem in terms of scaling?
Actually, we have, as I mentioned, we have device different dimensions as well. So the data that we had like 1 micron, 2 micron, and 4 microns. These are the three data we had. But for our logic circuit design and also for our memory application, because we will have to drive the memory element using this heater pattern device, and we need this suitable current level that we need. So for that, this 4 micron device was suitable. That's why we used that. But we had different dimensions as well.
Okay.
Yeah.
And those compatibility with squid, is that why 4 micron is desirable?
Yes, because of the current level that we need. And again, we can also like play with other dimension as well to get the same current level, but the scalability is not a concern, as I mentioned. We can go to lower dimensions as well for this device.
Maybe just to add one, excuse me, quick comment. Depending on the type of superconductor you use to make this electron devices, those current levels will also change.
Yes,
So
yes.
we were kind of
So-
limited by what our experimental collaborator could provide. in the
Yeah,
end.
yeah. So the material that they used here was tungsten silicide as the superconducting material, but there are experimental data for the same device with niobium nitride, niobium, and all those other superconductors as well. And there, in some cases, we have different current levels, different resistance levels. Also, their speeds also vary. Like the switching speed also varies. So yeah, we can have different options.
I guess in summary, these two devices need to be co-designed carefully, depending on what the AP squid asks for to design the H-tonic or vice versa.
Yes, yes. So that's what we did in our work. So we tried to co-design both this AP squid and heater fraction to design different competing components, and we tried to solve some of the existing challenges. So first, we developed a AP squid based memory system. So here again, the definition of memory states is completely similar to the conventional ferroelectric memory. So we use two polarization states to store the memory states, logic 0 and logic 1, and the write operation is also similar. We need to apply either a positive voltage or a negative voltage across this ferroelectric material to switch between these two memory states. But for the read operation, we use this squid or the superconducting portion here, and for that we need to apply a suitable current to the squid. And we need to choose this current very carefully because that must be in between the two critical current levels that we have for two polarization states of the ferroelectric material. Now, for the negative polarization, if you look at this blue curve here, you see the apply to read current is less than the critical current that we have. So we have superconducting behavior from the device, which is 0 voltage drop. And for the positive polarization, which is logic 1, here you see the applied read current is greater than the critical current. So we have the resistive behavior, which will give us some non-zero voltage drop. So as you can see from the read operation here, we get directly binary decisions, 0 voltage and non-zero voltage for the two memory states. So for these memory systems, we don't need any peripheral circuitry or sense amplifier to detect the memory state here. And as I mentioned, this ferroelectric material will give us non-volatile, which will be good for long-term storage. And also because of this superconducting device, which we use for read operation, our read operation will be extremely energy efficient. And also, unlike any Josephson junction based existing superconducting memories, we will not need any inductors or inductive coupling in this memory system. So we'll have higher scalability. And also, as I explained, in our memory system, we can use only one device to store 1 bit of data. But as you can see in the existing memory cell design, we need multiple Josephson junction, multiple inductors and inductive coupling to store 1 bit of data. So with our memory system, we'll have higher scalability compared to the Josephson junction based memory systems. And also, as I've explained, for write operation, we need to apply a voltage across the ferroelectric material. And for read operation, we need to apply a suitable current through the squid. So we have two completely separate paths for the read and write operation, which will allow us to optimize any of these operations without any mutual conflict. And that will provide unique advantages for in-memory computing applications, which I'll discuss in one of the next slides. So this is the schematic of the memory array for this EpiSquid based memory system. Here again, we use this heater fraction device as the access device for the read operation, because for write operation, we again use the conventional V/2 biasing technique, which is used for ferroelectric memories. So we apply these voltages to this rightward line, red lines, and the green lines, source lines, in a way so that only the access cell gets the complete voltage, and the cells that are in the same row and in the same column with the access cell will get the half of the voltage, which are called half access cells. And the cells that are not in the same row or in the same column will get 0 voltage across them, which is the unaccessed cells. And we have to choose the right voltage here very carefully so that half of that voltage cannot actually switch the memory state stored in those half access cells. And when we maintain that with this biasing scheme, we can actually write into one specific cell in the array, and we can keep all the other cells undisturbed. And for the read operation, again, we use this gate current control channel of switching of the channel of heater fraction device here. And we apply currents to this read word line and read bit line in a way so that only the read current only flows to the access cell. And then we will get either 0 voltage or non-zero voltage based on the memory state stored in there. Then we use this compact model of the EpiSquid and the lookup table based model of heater fraction to develop this simulation framework. And we simulated this memory read and write operations. And here you can see that although the half access cell get half of that voltage, but that's not sufficient to switch their state. That's why these HA cells here in the bottom figures, they remain in their previous state. Only the state of the access cells switch to the intended state here. And again, for read operation, we get again these binary decisions from this memory system. Then we use this.
How are you generating the read current? Where's that supplied?
Yeah, here we assume that we are applying the read current directly to the read word line.
Still kind of current control for read operations.
Yes, but we will need peripheral circuitry for that, and
Right.
yeah, and that's actually used in like superconducting circuits. So we need that, but here we also designed the memory array in a way that the current cannot be divided, right? So when we try to apply this current through one branch, we made sure that the current flows through that branch, that doesn't go to other branches because of the superconducting nature of heater fraction. Because if we have two resistance states, the current can be divided. But here we have completely 0 resistance state from some heater fractions.
Right.
So that will take the
There's
whole
some
current.
peripherals. And I'm probably getting ahead, I apologize.
Yeah.
But is that the peripheral, like the power and everything for generating that current, sourcing the current, is that included in your kind of system level power estimates later?
Here it was not included, but that's a challenge, as I already mentioned, the current bias. But like if you whenever you use any superconducting device, you will have to like deal with current biases. So that's actually a challenge, but yeah.
But what is, sorry.
Okay, no, that's no problem. Well, first of all, I want to make sure that Dr. Rose's question got answered. So, okay.
Yeah.
So, in terms of these peripherals and the current control, is there, because you're obviously a lot more familiar, you're very familiar with the literature. It seems like there ought to be some effort to use existing current controlled logic as peripheral support interface with that. And it seems like to me that can be, especially a form of logic that is extremely code capable. That ought to be, I'm just throwing that out there as a potential opportunity.
Yeah, yes. Like there are like many works who actually designed this peripheral circuitry to supply these currents that we need in different circuits, like logic circuits or memory circuits. So how can we deliver these currents? Like one of them is current splitter, where you apply one current and they generate multiple currents of the same magnitude. And then you can take that to different circuit, like different input of the circuits. So there are like different versions of that current splitter and also similar peripheral circuitry, which you can use to apply this type of currents. But this is true, you will like have higher overhead to apply this current compared to voltage biases.
Just want to highlight, do you want to talk about how your current control array is different from the existing superconducting memories that also use current control? Despite them both appearing current control, there is a, I think there is a big advantage.
Yeah. So obviously, yeah, as I mentioned, like here, if you look at this existing memory array based on Josephson mentioned there, we need multiple current biases. That's the first thing. And also we need to choose suitable combinations of these bias currents for different write operation, true write operation, and also the read operation here. So that's one of the challenges here. But here we are only using the current for read operation. But we are using voltage biases again for write operation. So we have some improvement there. We will get some better performance from that. And also you see there are inductors and inductive coupling because of this current biases, and you need to control this combination through this mutual coupling of inductors. But in our case, we use this heater correction device, which actually gives us that control. So that can control the direction of the current flow in this memory array, which you can see the design of these memory cells are completely like much simpler compared to any of the existing designs here.
I guess getting rid of the inductors is probably the biggest thing that you can claim in terms of area efficiency. Because you must have seen so many inductors, and if you have to put them on chip, they take a lot of area.
Oh, right.
Yeah, and also
if you go to the previous slide.
Yeah. And also the memory cell that you see, that's volatile. That's volatile. So, and the read operations are not like destructive here. So you'll have to do the write operations after like each of the read operation. But in our case, the device is non-volatile and the read is non-destructive. So that's another advantage.
Yes, the ferroelectric is.
Yes, ferroelectric is non-volatile. Yeah, that's storing the data.
So all this hard work to get this one memory cell working, but still volatile. And then
yes. And with this, as I mentioned, the scalability is a major concern because of these inductors and the large cell size. And the highest memory that could be demonstrated experimentally with this Josephson junction technology had a like storage capacity of 60 kilobits, 16 kilobits so far. You see, like like within a 5 by 5 millimeter square chip. So you see that that's of no use because of the storage capacity that we have. And the major challenge is again these inductors and like the large cell area to store 1 bit here. So I'll move to the second portion where we use the same ferroelectric squid device to design voltage control logic family. So as I explained, this ferroelectric material gives us voltage control over the switching of the superconducting device, which we used here to design voltage control logic circuit. So here our goal was to avoid this hysteresis region of the ferroelectric. So we represented the logic 0 and logic 1 inputs in a way so that we can either be in the negative polarization state or in the positive polarization state, so that when we apply the suitable current through the squid, we'll either get a superconducting state or a non-superconducting state. So when you get the superconducting state, that will take the whole current through it. And when you have the resistive state, it will drive the current, almost all the current, to the external circuitry. So we have this switching behavior here. So we use that switching behavior to design all the basic logic gates. And I will not talk about the working principle of all the logic gates. I'll only talk about the AND gate here to give you some idea how these logic circuits operate. So here, just to remember, for logic 0 input, we have negative polarization in the ferroelectric, which gives us the superconducting behavior from the squid. And for logic 1 input, we have the positive polarization, which gives us the resistive behavior from the squid. Now, in the AND gate, we have two ferroelectric squids connected in parallel. Then we have this external resistor, which will have much lower value compared to the resistive state of the squid, so that it can take almost all the currents when both the squids become resistive. And after that, we have this heater correction device again. So the purpose of this heater correction device is here is to convert the output voltage to the same level of the input voltage, so that we can again seamlessly connect multiple logic stages. So for the logic 0-0 condition here, you see both of the FE squids will remain superconducting, so they will take the whole current through them. So the external resistor or the gate of the heater pattern that you have later will not get any current. So they will remain in the superconducting state, and we will have logic 0 output. Similarly, for 0-1 or 1-0 condition, one of the FE squids will remain superconducting, and that will take the whole current here. Again, the gate of the heater correction will not get any current, so the channel will remain superconducting again. Finally, for 1-1 condition, you see both of the FE squids will become resistive. So now, since we have very low resistance in the external circuitry, almost all the currents will be driven towards the external circuitry, and the gate now will get gate of the heater correction will now get sufficient current, and the channel will switch to the resistive state. And as a result, we will get logic 1 at the output here. And as I mentioned, with the same working principle, we could design all the basic logic gates like inverter, AND gate, and OR gate. And we also designed this copy gate, which is like the buffer. And as you have, since you have voltage controlled input and output in this logic circuits, we have larger number of fan out like CMOS logic gates compared to the current control logic circuits. And also, as I mentioned, using this heater correction, we made sure that we get the same level of voltage in the input and the output, so that we can drive the next stage logic, inputs of next stage logic with the output directly. So we have better cascadability here as well. So to show this fan out and cascadability features, we use this basic logic gate to simulate this XOR functionality. Again, here you can see we are having higher fan out and higher cascadability here. So we verified this functionality of this logic gates and this XOR functionality in simulation using those complex models again, which are calibrated with experimental data. Then we
Sorry, so you go back, please. So you have a lot of DC current, and you've alluded to this before, you have a lot of DC current overhead.
yes.
And I guess at this point of the technology development, that's not a big concern because you're just trying to demonstrate this.
Yes.
Right, I
yes.
mean, it reminds me of the, like first Cray computer was very high powered. As a matter of fact, they had to use liquid nitrogen not to get the high operating speed, but to keep the chip from, or to keep the electronics. It wasn't one chip. It was a bunch of ECL gates and then a couple of logic.
Yeah.
To keep those from melting.
Yes, but again, like the advantage here is the biases, current biases that we are applying is like constant current bias. So
Well, it's the same thing with ECL.
Yes,
It's
yes.
constant current
Yes,
bias, and
yes.
you steer between.
But in the existing current control logic circuits, the inputs are also current control. So for example, if we look at this here, we are connecting this input to two different nodes. Now, since if we have current control input, we will not be able to do that. So we'll have to generate those two same currents, like from peripheral circuitry, like other circuitry. So that will have again huge overhead. So, or we'll need those current splitter circuitry. But the advantage we are like, because of the superconducting device, we always need these current biases, but we are getting rid of the current control input or output here, which are giving us these better fan out and cascadability features. So then we also use the FSQ based memory systems to perform matrix vector multiplication in the in-memory computing feature nature. So we all know that in-memory computing systems gives us a better energy efficiency and better performance compared to the von Neumann architectures, because they reduce the amount of data movement between the memory and processing units to perform any computing task. But when you consider the cryogenic environment, we get a unique advantage here, which is, as I mentioned, to achieve and maintain a cryogenic environment, we need to use cooling refrigerator and we need to keep supplying the coolant there. And as you can see in this right figure, the amount of coolant increases exponentially with the power consumption of the system that we are cooling. That's why we also have that upper power limit. But if we have an in-memory computing system, we will be able to reduce this power consumption of the system in the x-axis. That will help us to reduce this cooling cost. That's why energy efficiency is a crucial thing for cryogenic environment to have lower cooling costs. So we use this, and also it has been recently shown that different machine learning algorithms can be useful for the control and the quantum error correction of qubits in quantum computing. So again, if you want to have machine learning algorithms, the von Neumann architecture will not be efficient at all, because in machine learning algorithms, you need a huge amount of data movement between the memory and processing units. So if we have a suitable cryogenic computing, in-memory computing system, that can also be a solution for this machine learning algorithms at cryogenic environment. So we use this FSQ-based memory system to perform this matrix vector multiplication, which is again the most frequently performed operation in any machine learning algorithm. So we represented the input matrix with different levels of read currents that we apply to the rows of this memory array. And we represented the weight matrix by the memory state stored in this FSQ cells in each column. And then we designed this custom peripheral circuitry because based on this input and weight matrices, we get different levels of voltage in different rows of this memory array. So we use this custom sense amplifier with two voltage comparators and a multiplexer, and we also designed the Josephson junction FET-based superconducting voltage comparator, which can be used here, and that also is compatible with the voltage levels that we get from this memory array. And with this peripheral circuitry, we could actually get the matrix vector multiplication result from this memory system. And again, after storing the weights in this memory system, which are the write operation, when we perform this matrix vector multiplication, we just perform the read operation again and again. And as you remember, in this memory system, we use that superconducting portion for the read operation, which is highly energy efficient. That's why we have estimated here to perform 1 bit of matrix vector multiplication, we need around 5 attojoule of energy, which is significant improvement in compared to any other memory technologies that we have. Then we also perform different classification tasks with this in-memory computing systems. I actually worked with a CS student from our group who is also here, I think, Jack. So he developed a Python framework and that was calibrated with the working principle of FSQuid device and FSQuid based memory system. And with that hardware software co-design framework, we actually perform different classification tasks. We first perform the hand-written digit recognition, where we encoded the input digit with different levels of read currents. Again, here we could optimize this encoding as much as we wanted because we have that separate read-write path capability. We don't have any mutual conflict here between the read and write operation. And then we did the training operation to generate the weights to classify different digits. And we applied this constant here that when we generate these weights, they must be in terms of 2 resistance states that we get from ferroelectric material, ferroelectric squid device, so that we can store those weights directly in the memory array. And then using this peripheral circuitry and also the winner-takes circuit, we could predict the digit here. So this is the confusion matrix for this digit recognition task. And as you can see, we got reasonable accuracy for classifying all the handwritten digit. And we also explored how the number of rows for input mapping and number of columns for storing the weights affect the classification accuracy. And as you can see, this gives us some trade-off between the classification accuracy and the memory size that we need for performing this task. We also performed 2 other classification tasks with fashion dataset and the sentiment text dataset. And for both all these classification tasks, we actually got reasonable accuracy using a reasonable, realistic size of memory system. And finally, we also compared this with existing room temperature memory strip approaches because we don't have sufficient work, some cryogenic in memory computing for this classification task. And we also know that the memory strip memories and FSQuid based memories operate at 2 completely different temperature ranges. So they're comparing their energy efficiency and speed will not be fair because again, like FSQuid memory system will always have better energy efficiency compared to the memory strip memories. We only considered accuracy in terms of comparison, and as you can see here, we got better accuracy in all the classification tasks. And one of the reasons behind that is the separate read-write path capability of the memory system. So when we, after storing the weights, when we try to perform the matrix vector multiplication result, we optimize the read operation as much as we wanted. And we made sure that we get highest amount of distinguishability in the decision-making step. But in the memory strip memories, we don't have that freedom because there we use the same path for read and write operations. So the read voltage must be less than the switching thresholds of the memory strip. So we have some limitations there. And then we also use this FSQuid based device to design a content addressable memory. So content addressable memory is a different version of memory system. In conventional memories, we provide the address as the input and we get the data back stored in that address. But in content addressable memory, we actually provide the data as the input and we get the address back where that data is stored. So there are 2 types of content address memory. One is binary CAM, where we only have zeros and ones for the data and search bit. And we have this ternary CAM, where you can introduce a don't care condition in the search bit, which allows you to do some while search. So these content addressable memories allow you to search through the whole data set that is stored in the memory array by like for any query that you want. So that you'll have to just apply that query as the search bit, and that will give you the matching or mismatching result from the whole data set. So that's why they are really useful for different machine learning and AI algorithms, and because you can search through the whole data set here in single cycle. So this is the schematic of the FSQuid-based TCAM cell, which is where we use actually 2 memory cells connected in parallel to design 1-bit TCAM cells, because here we store both the data and the data bar, and we also need to apply both search and search bar to get this 1-bit TCAM operation here. And the bottom figure here shows how we can connect these TCAM cells in parallel with each other in the row in an array scenario. So this TCAM cell has 2 different modes. The first one is for exact search, where we use the superconducting and resistive switching of the FSQuid device. and that's completely similar to the memory application. So here we get, as I will explain, here we get again the binary decision for matching and mismatching condition. And we have another mode to calculate the Hamming distance where we avoid the superconducting state of the F-squid, because if when you connect these cells in the row in parallel, if one of the cells becomes superconducting, the whole row will become superconducting. So we'll not be able to calculate the Hamming distance here. That's why we avoided that superconducting region, and we use these two resistance states for two polarization that we get from this device to calculate this Hamming distance. And for defining the search bit here, we apply the currents to the gates of these two heterocryoctrons. And for 0 and 1, we actually apply opposite combinations so that these two heterocryoctrons, one of them will become resistive and the other will remain superconducting. And for don't care condition, because in don't care, we always want matching condition. That's why we applied positive current to both the gates of heterocryoctrons so that both of them becomes resistive in that condition. So this slide here shows the working principle for the exact search mode. Let's first consider, talk about the mismatched condition where you have different data and search speeds. And as you can see, because of these biasing conditions and data representation, one of the two parallel branches become completely superconducting for this mismatching condition. So now if we measure the read word line voltage here, you will get 0 voltage because one of the parallel branches is completely superconducting. So for any mismatching condition, you will get 0 voltage from this TCAM cell. And if we look at the other conditions where you have the same data and search bit, or you have don't care in the search bit, which are considered as the matching condition, you see that none of the parallel branches become completely superconducting, where we get some resistive component in each of the branches. Now, when we measure this read word line voltage here, we will get some non-zero voltage, and that might be different. But the point is here, for mismatching condition, we get 0 voltage, and for any matching condition, we get non-zero voltage, which is again the binary decision here. And if we only care about exact search, we can use only the TCAM memory array. We don't need again any sense amplifier or peripheral circuitry, which we need for any other memory technologies like memory strip, ferroelectric TCAMs. And finally, for the Hamming distance calculation, as I mentioned, we need to avoid this superconducting behavior. And if you look at this IV characteristic, you can see when we go to the resistive state for both the polarization states, we have two different slopes. That means when for two polarization states, the device will show two different resistance states. That's what we use, and that's again like memory strip behavior. That's what we use to get analog voltage level for the Hamming distance calculation. And here we will need peripheral circuitry to decode this Hamming distance. And as you can see in this blue region here, we consider a 4x4 TCAM array, and for different amounts of mismatch, we get different levels of voltage, and we can use that to decode the Hamming distance from here.
And could you explain what Hamming distance is?
So Hamming distance is the mismatch, amount of mismatch between the search and the data bit. So if we have 4 bit of data and 4 bit of search, if we have 1 bit mismatch, Hamming distance is 1. If we have 2 bits mismatch, Hamming distance is 2, something like that. And if you have complete matching, so we will have Hamming distance on 0. And we also consider this high bits, high number of memory array, high size for the memory array, and you see that for different degree of mismatch here, for each of the conditions, we get different levels of voltage, analog voltages. And another advantage here is that when I mentioned that we connect the TCAM cells in the array scenario in parallel with each other in one row. Right now, when we have this 4x4 array, if one of the TCAM cells become superconducting, since they are connected in parallel in the row voltage will become 0 voltage. And that's what we see here. You see if there is 1 bit mismatch, that will give you 0 voltage. And if you have 2, 3, 4, that doesn't matter. If you have any degree of mismatch in the exact search mode, that will give you 0 voltage. And if you have complete matching condition, there you only have this non-zero voltage. So that's again really useful for doing the exact search to get the matching and mismatching result here. So this is one of the advantages of this F-squid-based TCAM because of this superconducting behavior, which we get when we connect these cells in parallel. And another advantage is that if we compare this F-squid-based TCAM with any other TCAM technology, we will get a significant improvement in energy efficiency. And that's what we are trying to do. We are trying to use these TCAM cells to perform some system level applications. One of them could be hyperdimensional computing, where we need to perform this TCAM search operation in a large scale. And we have seen that if we compare this with cryogenic SRAM-based TCAMs, we get at least 1,000 times improvement in energy efficiency compare with this epi-squid based TCAM because of this superconducting behavior that we have. Because in one state we have zero energy consumption because of that zero resistance.
This is all simulation, right?
Yes, yes.
So do you have any kind of feel for like in a practical system, how repeatable would these results be? Because these are pretty small voltages.
Yeah, as you can see, like here, like when we go to large scales, the voltage difference becomes lower actually. So that's the challenge. But what we can do here, another thing, like we have a trade-off here. So let me go back. So here, if you see, like for the Hamming distance, we need to operate at this resistive state. But here we only use 5 microamps of current to go to this resistive state. But if we again increase the current, that will have higher power consumption, but that will give us some better distinguishability between these voltages, like between these voltages that we get for different degree of mismatch. So if we go to like higher memory array, we can use that to get better distinguishability.
So with more power, you would get more noise margin.
Yes, yes, more distinguishability.
That's how I'm interpreting what you're saying.
Yes, yes.
Okay.
So finally, we also use this heater pattern device to design the reconfigurable logic circuit. As I explained, in heater pattern, we have this gate current control switching of the channel. Here, this is the measurement method that our collaborator from NIST used. So they first apply a constant current to the channel of heater pattern, and then they start increasing the gate current. So when they don't have a sufficient current in the gate, the channel remains superconducting. And as a result, you see, we don't have any current through the external circuitry. So the superconducting channel here takes the whole current. So as you can see, up to this point, before the red line, we don't have any current through the external resistor, which means the superconducting behavior of the channel. And when we have sufficient current in the gate terminal, the channel switches to the resistive state. And another advantage of this device is that compared to any other superconducting devices, this device shows very high resistance when it becomes resistive, and it can show mega ohm ranges as well in the resistive state. That's why it can drive almost all the current to the external circuitry. Here, that's what we see when it becomes resistive. The external resistor gets the whole current, almost the whole current, and we have some non-zero voltage drop in the load resistor here. So we use this gate current control switching of the channel to design this reconfigurable logic circuit where we took advantage of this current summation phenomenon. So in the gate, we used multiple input terminals corresponding to the number of inputs of the logic operation that we want to perform. And we have this another biasing condition, IB1, which will determine if we choose the different values for IB1, that will determine different logic operations here. And this table here shows how we can choose the suitable value for IB1 to perform different logic operation. And here we only considered up to 3 input logic operations. That's why we have 3 input terminals. Again, this logic circuit is completely current control, like the existing current control superconducting logic circuit. So all the challenges that we have will be there in this logic circuit.
So what's magical about 55 microamps? Why not 50 microamps?
So that's coming from the switch gate critical current that we have. If I go back, so when we have this characteristic from this device for every,
I'm sorry, now I see it on.
for every specific channel current, we have a gate critical current. So that's what we use, half of that gate critical current. And if we have different critical current, that can change. But for our case, that was 55 microamps. So I will only talk about how this copy gate or the buffer operates. So for copy gate, we need to apply 65 microamps current to this IB1. This is a constant current. And then when we consider the logic 0 input, we apply 0 microamps current. As a result, the gate here only sees a total of 65 microamps current, which is less than the gate critical current. So the channel cannot switch to the resistive state. It remains in the superconducting state, and we don't get any current in the output. So you have logic 0 as the output. And for logic 1 input condition here, we apply the 55 microamps to the input terminal. Now the gate sees a total of 120 microamps current. And that's greater than the gate critical current, which is 110 microamps for this case. And the channel switches to the resistive state, and we have logic 1 at the output. Using the similar mechanism, we could also perform the 1 input inverter, non-AND gate, OR gate, and 3 input majority gate. Here, we only had to choose different values for this IB1 to perform these different logic operations. Again, the advantage of this reconfigurable logic circuit is that the better area efficiency, because you see we can use only one device with multiple input terminals to perform up to 3 input logic gates. But in the left figure, you see this is one of the existing heater pattern based logic circuits where the number of devices actually increases with the number of inputs of the logic operation. But in our case, we can use only one device to perform up to 3 input logic operations. So we have better area efficiency and also better energy efficiency from this logic circuit. And also another advantage is that when you have this reconfigurable circuit where we can use the same layout to perform different logic operations. We don't need to change the circuit design. We just have to choose suitable biasing conditions to perform different logic operations. Now, when you use these circuit blocks to develop a large system, from the layout view, each of these blocks will look identical. Because if you don't know the suitable biasing condition, you cannot reverse engineer the system. But from CMOS layout, you can have some idea to identify which portion is performing what logic operation. Yeah. But here we cannot do that. That's why we have a better security against reverse engineering attacks, and you can design this camouflage logic system, they call that. Yeah. Now I'll move to the second part of my presentation where I'll talk about how we use these topological devices to, again, for cryogenic computing. So we use this quantum anomalous.
Sorry for interrupting. Before we move on to the next phase, I just had a quick question. All these devices, all these new circuits with ferroelectric suite, in your opinion, what is the biggest limiting factor now for FE suite based devices and circuits that you have developed?
Yeah, so there are like different challenges in different applications. So again, first in the memory system, the challenge is like again the scalability. Like we don't know how these memory cells will work if we have a like larger memory system like 64 or 128 or even 512 by 512. We don't know that. We'll have to experimentally demonstrate to like have some idea about that. But both of the device like FE-Squid and heater cryotron were experimentally demonstrated, and they have like compatible performance that we can use to design this memory system. And for logic circuit, one of the major challenges that we observe is the switching voltage of the ferroelectric material. So the ferroelectric material that we used, lead zirconium titanium had a coercive voltage of plus minus 4 volt. So that's again like large voltage, and that was one of the limiting factor for the logic circuit, because we need, if we have like plus minus 6 volt at the input, we also need that plus minus 6 volt at the output. And to generate that, we had to like spend like large power. But if we have a ferroelectric material that can like switch with like 1 or like less than 1 volt, then that will be like significantly improvement in terms of power consumption, energy efficiency of the whole logic circuit.
So what you're saying is possibly switching to other ferroelectrics like HZO, for example.
Yes. Hafnium zirconium oxide actually shows switching at lower voltages, but unfortunately, we don't have the experimental data for that ferroelectric squid device with hafnium zirconium oxide. We only have like ferroelectric squid device with PZT. That's what we used here.
So as you're having to increase that voltage that you mentioned, the assumption is that the current level is not changing. So therefore, that's why you said it's more power, because you still have all the current overhead. That's not changing, but you're having to increase the voltage to try to support a larger array.
Yes.
Am I correct in understanding that's why it's higher power? Because I mean,
yes, higher power is coming from the conversion process. So after when you do this conversion to match the output voltage with the input voltage, there we need to spend higher power, because we need to go to that like high voltage plus minus 6 volt at the output as well. So heater cryotron actually is doing that conversion in the logic circuit. But as I explained, the heater cryotron has like high resistance. People have shown like mega ohm level like resistance, but that can actually, that's also used as an interface between CMOS and superconducting circuits in different papers. But the challenge is like, again, we need high voltage because of this ferroelectric.
yeah, I was just pointing out that, higher voltage is not necessarily higher power. It depends on what's happening with the current.
Yeah, obviously, because like in the heater cryotron, when you have resistive state, you'll have to apply the suitable current to get that voltage. So that will actually increase the power.
I think there was a question.
My question is, so you don't combine ferroelectric layers with superconductor, right?
Yeah.
So is there any way to simulate what's going on when it comes to like integrating more like in the interface? Can we simulate circuitry, the circuitry behavior of the interface?
Yeah,
Is
yeah.
there any like circuit that shows that when you combine these two technologies, which one is the firing behavior of them and other is superconducting? By that, what happens?
So I'm not sure about the circuitry, but we can obviously do some device level simulation to observe the behavior in the interface. That's what people have done already. Like for ferroelectric squid, you have ferroelectric, which is non-superconducting. Then on top of it, you have the superconducting device. And in the interface, the charge density actually changes based on the polarization state of the ferroelectric, and that's what dictates the like the superconducting behaviors of the superconducting device. And people have done that, try to simulate that what happens in the interface to observe what happens like in the eventually in the superconducting device.
Question was the physical, the physics element that's going on in the interface. Can you convert it into the circuitry? Is there any like how to?
So that's what we do actually. Like we first simulate in the device level, we try to understand what happens in the interface, and we try to understand the physics for that. And then we use that physics or the behavior in the device level model. Like, but that's also like a high level model, not again using all the physics, but we try to capture that physics in the device compact models that we design. And then we use that compact model for the circuit level implementation. But I'm not sure if there is any tool where we can do all this like interface level simulation for circuits. But there are ticket tools, console tools, which we can use to simulate like device level, what happens to see what happens in the interface. But in the circuit level, we always take the physics understanding from those tools, and we develop compact models, which is sort of some sort of approximation in some cases, and then we do the circuit level analysis.
There is no existing circuit which shows the combination of both elements, right?
The circuit simulations that we do in Cadence or Spice that shows you the the co-design between these two devices. Yeah, but we don't care like look into the interface directly during the circuit simulation.
You know, what you're saying reminds me of a very painful part of my youth where I was doing gallium arsenide circuits. And that material is piezoelectric. I mean, it sounds to me like you're really alluding to what's the influence of the material properties on circuit performance.
Yes.
And I would see situations where if you have two identical gallium arsenide chips, they're packaged in two different chips, two different packages. And one of them would have different mechanical stress on it than the other, just a little bit, just a little bit. And it would impact, circuit performance. It's an incredibly aggravating thing that later requires therapy. But anyway, but what you're alluding to is a very powerful, I would imagine, a very powerful need.
Absolutely. And maybe just to add to your comment, one of the reasons why we dreamt of doing that, like going all the way from material parameters directly linking circuit. So right now we do it indirectly. We basically first put it in a device model and then run the device model in circuit. There is no direct link between them. One of the reasons is our experimental collaborators told us many of this underlying physics of superconductor ferroelectric interplay is not well understood. And even if you try to model them, it will probably be an incorrect model or substandard model.
It's going to be a guess at the best.
Yes. So rather than doing so, our strategy, I think Shamiul's strategy was to completely rely on experimental data so that you know what you're getting is actually what you will get in experiment.
And then what we also end up doing is over designing the circuits
Right.
to help compensate for these things.
Yes,
Absolutely.
we also do some Monte Carlo simulations at some points to also take care of the variation. We do this Monte Carlo simulation.
That's a good point.
So in the second portion, I'll talk about how we utilize this quantum anomalous Hall effect phenomena in topological devices for cryogenic computing. We all are familiar with Hall effect, where in the presence of an magnetic field, when you apply a current to a material, we get a voltage developed in the longitudinal direction of the current flow. we call that the Hall voltage. And this quantum anomalous Hall effect is a sophisticated version of that Hall effect. Here, we don't need any magnetic field, and we just need to apply current to this material. And when we measure this Hall voltage in the longitudinal direction of the current, we see that the Hall voltage becomes quantized at different levels. And that's what is this quantum anomalous Hall effect. And this is the characteristics of quantum anomalous Hall effect, where you see the Hall resistance versus bias current behavior. You see we have this hysteresis, which can be non-volatile hysteresis, which can be utilized for memory applications. And this Hall resistance is defined by the ratio of Hall voltage and the bias current that we apply. So here, the idea is we use these two quantized Hall resistance states to define two memory states, logic 0 and logic 1. And again, we need to apply a positive current greater than the switching threshold for write 1 and negative current less than the switching threshold for write 0. And for read operation, we need to choose a current from this hysteresis, which will give us two different Hall voltage levels for the two Hall resistance states. So in our work, we use this twisted bilayer graphene Moire heterostructure, where we have two layers of graphene twisted by a very small angle, which is 1.1 degree. And the honeycomb structure that you see, that's the twisted bilayer graphene structure. And this is sandwiched between two hexagonal boron nitride layer on the top and on the bottom. And this is the Hall resistance versus bias current characteristics for this heterostructure. And you see here, we can switch between these two quantized Hall resistance states by applying nanoampere level of current, which will give us ultra low power consumption write and read operation. But again, that's difficult to control as well. And during the read operation here, as I explained, if we choose a current from this hysteresis region, here we chose a negative current, we will get positive Hall voltage for the logic 0 and a negative Hall voltage for logic 1. So we will need a voltage comparator to distinguish between this positive and negative voltage to detect the memory state stored in this cell. So this is the design of the memory cell that we came up with. So we connected this memory element, quantum anomalous Hall effect based memory element in series with this selector device. And as the selector, we use this MIC material based selector. And there are two major reasons of using this material. You can see the experimental relation between this current and voltage in this selector. And that's why they are also known as exponential selector. And the first reason for using this selector is that, as I explained, to write for the write operation in this memory element, we need to apply nanoampere level of current. And with the transistor or other selector device, we cannot control that current because that lies in the off state. But here with this selector, you can see that we can get this nanoampere level of current with a controllable amount of voltage, which is in the range of 0.4, 0.5 volt. So that's one of the reasons. And the other reason is from the array scenario. So for this memory system, we designed this 3D cross-point memory array where we sandwich that memory cell between one bit line and word line. And the voltage of these cells will be the difference of this bit line and word line voltages. So again, we use the V/2 biasing mechanism for the read and write operation in this memory system. And the way it works, when we apply these voltages to the bit line and word line, the access cell, which is shown by this yellow color here, will get the complete access voltage. But there are cells that are in the same row or in the same column will get half of that voltage. That's why they're called as half access cells, the pink one and the black ones. And the cells that are not in the same row and the same column, the red ones will get 0 voltage across them, and they are known as the unaccessed cell. Now we'll have to make sure that when this half access cell get the half of that voltage, that cannot switch the state of those cells. We'll have to make sure that. And that's where this selector becomes really useful, because to look at this IV characteristics for write operation here, we need to apply plus minus 5 nanoampere of current. And for that, we need to apply around 0.5 volt across this memory cell. And when we apply this, the half access cell gets half of that voltage. So it's 0.25 volt. And if you look at this here for 0.25 volt, because of this exponential relation, we get like picoampere level of current, which is not sufficient to switch the states of those half access cells. So that's the second reason why you use this selector here. So this is the schematic of the complete memory array, where we connected this memory cells between one word line and bit line, and we connected all the cells in a row in a way so that the row voltage corresponds to the summation of all the Hall voltages of all those cells in one row. And that's also becomes really useful for in-memory computing applications, which I will discuss in one of the next slides. And for the peripheral circuitry here, we use this amplifier and comparator because, as I mentioned, we get positive and negative voltage. So we need a voltage comparator. but the voltage levels that we get, whole voltage level here, that's in the range of microvolt level. That's and we cannot use any existing voltage comparator for that. That's why we have this amplifier to control that, convert that into the millivolt level voltages, so that we can use the existing CMOS voltage comparators here. But if we have any superconducting voltage comparator that can or other voltage comparator that can distinguish between two microvolt level voltages, we will be able to get rid of this amplifier, and that will increase the scalability and also the energy efficiency of this memory system.
I mean, isn't the voltage amplifier followed by the comparator basically those two blocks cascaded? Isn't that basically a sense amp?
Yes, voltage sense amplifier, but here we need like large amplification, actually 1,000 times, at least 1,000 times amplification. That's why we use the dedicated amplifier here, just to show that. Yeah, and you're right. Like if you combine these two, that will be
I mean, because the circuit there on the right.
Yeah.
I smell a sense amp.
Yes. Yeah.
Basically, just to add a backstory here, he was trying to look for off-the-shelf circuits that he could just pick and use, and he found an amplifier and the comparator. He just put the
Oh, of course. Yeah. That's what happens. Right. That's what happens.
So this shows the simulation results where we perform the write and read operations again, and we using that V/2 biasing scheme that I explained, we could perform all the read and write operation in one specific cell without disturbing all the other cells in the array. Yeah. So again, the advantage of this memory system is that, as I explained, we need to apply nanoampere level of current for read and write operations. Although that is difficult to control, but that gives us extreme power efficiency. We get ultra low power for the write and read operations. Also, the devices, the memory element and the selector that we use, they are highly scalable, and like in terms of cell area, not in terms of repeatability. So that's why we have smaller cell area and we'll have higher scalability. And finally, the Hall resistance, quantized Hall resistance that we use to store the memory states, they are topologically protected, because if you remember, they are represented in terms of plus minus h over e square, and h and e both are constant. That's why topologically protected, and that gives us better immunity to external variations. And when we compare these memory systems with existing other cryogenic technologies, we see that this has much smaller cell area, and also we will have much smaller power consumption for the write and read operation from this memory system. Then we also use these quantum anonymous Hall effect based memory systems to perform Boolean logic inside this memory system. And I've already explained the advantages of in-memory computing for cryogenic environment. So we had to develop a modified peripheral circuitry. The memory system was exactly same. We just have to change the sense amplifier here to perform this logic operations. And we wanted to perform the NAND, NOR, and XOR operation in single cycle. So NAND and NOR was straightforward, but to perform XOR operation in one cycle, we had to use this very complex sense amplifier where we have these two voltage comparators and one AND gate and one NOT gate. But we could perform the XOR operation in single cycle where we need multiple cycles for XOR implementation in inside any memory system. So here we simulated a 4x4 memory array, and we activated the first two columns and we stored the data in a way so that we can cover all the possible combinations. As you can see, the first row here gives us the 0-0 combination. The second, third row gives us 0-1 and 1-0, and the fourth row here gives us the 1-1 combination. And as I explained, we designed this memory array in a way the row voltage corresponds to the summation of the whole voltages of all the cells in that row, like all the activated cells in that row. And as a result, when you simulate this, you see that in the first row, we get positive voltage because both of these cells have positive Hall voltage. The second and third row gives us 0 voltage because one of those cells have positive voltage and another has the negative voltage with same magnitude. And the fourth row here gives us negative voltage because both of the cells have negative voltage, and when they are added, we get negative voltage. Then we use that sense amplifier, and when we enable that by choosing suitable reference voltages for those two voltage comparators, we could perform this NAND, NOR, and XOR operations for these two input condition here. So we also perform the Monte Carlo simulation to show the advantage in terms of immunity to variations coming from the topological protection here. So for any memory system, we have two sources of variation, mainly one coming from the biasing side and another coming from the resistance state that we use to store the memory. But here, as I explained, the Hall resistance state that we use, they are quantized and topologically protected. So we have better immunity to variations up to a certain condition. on that. So we only used Gaussian variation for the read current that we applied to the memory array for performing this memory task. And you see that even though there are some sort of variations, but for the two input condition, we have that similar distinguishability. Like for 0, 0 condition, we have positive voltage. For 0, 1 and 1, 0, we have 0 voltage. And for 1, 1 condition, we have negative voltage. So we will be able to use the same reference voltages, and these logic operations will work perfectly, even if there are some sort of variations in the biasing condition. Then we also finally also use this quantum anomalous holophilic based memory to perform majority operation, where the design of this memory array and the quantum anomalous holophilic phenomena together gives us a unique advantage. I will explain that here. So the majority is a logic operation which tells you if there are more number of logic 0 in the inputs or more number of logic 1 in the inputs. So if you have more number of logic zeros, the output will be logic 0. And if you have more number of logic 1 in the inputs, the output will be logic 1. And the advantage of majority logic is that you can use this majority logic to perform other logic operations as well. If, for example, if you put logic 0 to the third input, the output will correspond to the AND operation of the other two inputs. And if you put 1 to the third input, the output will correspond to the OR operation. But when you try to perform the addition, which is an integral part of arithmetic logic unit in any processing system, we get useful advantages from majority logic. As you can see from these equations, we can just perform 3 input logic, majority logic between A, B, and carry in to calculate the carry out. And if we have an inverted version of the carry out result that we calculated, then if we can perform this 5 input majority logic, we can calculate the sum result, which simplifies the logic circuit significantly, and we only need 3 logical levels here. And if we compare these with the NAND or NOR based implementations, we will need 6 and 7 logical levels for that. And when we map this into the memory array for in-memory computing applications, you see that for NAND or NOR based implementation, it has been reported that they need 10 cycles to do this addition. But with majority logic, we only need 4 cycles to do this addition here. And this is well known. It has been used in different memory systems to perform this majority based addition. And to summarize, the majority based logic provides you 57% needs lower logical levels, and also for in-memory condition, this majority based implementation need at least 60% lower cycles.
Yeah,
But yeah,
sorry, as you go back to that, just FYI, there's a lot of majority, we call it voter circuits.
yes,
Used in radiation hardened digital systems to provide immunity to single event upsets,
Yes.
where a bit split due to an ion strike.
yes.
So it's pretty common there, but I'm curious is, the attraction to NOR and NAND, I mean, those are computationally complete in the digital world.
Yes.
And so, you can readily describe it at the RTL level. So what about this majority scheme? Does that still translate at the RTL level?
Yeah,
There's a hardware restriction
majority with an inverter is also considered as functionally complete. If you have an inverter and majority logic, you can implement any Boolean logic function.
Oh,
with that.
okay. That's what I was just checking. All right.
Yeah.
That's a great point, Ben. We should probably also highlight that,
Yeah,
the
yes.
voter circuit.
Without the inverters.
Yeah.
It's
With,
really
along with an inverter, majority is also functionally complete. So when we try to perform this majority operation inside our quantum anomalous holophilic based memory, we observe a unique advantage. I will explain that. So here when we try to perform this 3 input majority logic, again, that coming from the quantum anomalous holophilic phenomena and the way we designed this memory array. So if you remember, in each row, we are connecting the memory cells in a way so that the row voltage corresponds to the summation of all voltages of all the activated cells. And when you activate these 3 cells in each row, you see for different logic combinations in this table, we get positive voltages for a more number of logic zeros and negative voltages for more number of logic ones, because we have positive voltage for logic 0 and negative voltage for logic 1. So we have the same distinguishability like the memory application. So when you try to perform majority operation, we don't need to change anything in the memory system. We can use the same simple voltage comparator to perform the majority logic operation. And when we scale to the larger number of inputs, like 5 input, you see we have the same trend here. For more number of logic zeros, we have positive voltage, and for more number of logic ones, we have negative voltage. So for any number of majority operations, we will be able to use the same memory system with a simple voltage comparator, and that will give us the majority result here. And here, this is how we perform the addition operation using this memory system. So we first need to activate the first three cells where we have this A, B, and carry in stored. So if we perform the majority, three input majority will give us the carry out, and then we need to store the inverted version of the carry out in the next two cells in that same row. And then if we activate these five cells, that will give us the sum results to the five input majority. And to do this, we will need total 4 cycles here to perform this addition. And again, as I mentioned, if we compare this with any other technology to perform this majority logic, this quantum anomalous Hall effect based majority logic gives a unique advantage from the behavior level. The first one is like, let's consider memory strip technologies to compare. So we know in memory strip memories, we have 2 different current levels for logic 0 and logic 1 from the high level. And if we want to perform 3 input logic operations, in the top figure, you can see we will get this type of different levels of current for different input conditions. And we'll have to distinguish between these 2 marked current levels to get the majority result. So we'll have to use a current comparator with a suitable current reference. But in our case, we have these 2 levels of voltage. Also, we have distinguishability in terms of polarity. So we have positive voltage for majority 0 output and negative voltage for majority 1 output. Now, if you have some sort of variations in this memory system, the memory strip memory, this current level will also change. So you might also have to change the reference current to get this majority output. And in some cases, in worst case variation, the circuit might also fail because of these 2 current might overlap because of variation. But in our case, we'll always have this difference in terms of polarity. So we will that will operate perfectly here. And another advantage is here, as I explained, in our system, when we go to large number of inputs for this majority operation, we still have this same distinguishability in terms of positive and negative voltage. So we can use the same voltage comparator with same reference, but in memory store, you see the 2 level of currents that we need to distinguish between will also increase with the number of inputs. So we'll have to change the reference current that we'll have to choose that reference current again for each of these input conditions to get the majority result. So which is again another unique advantage coming from this quantum anomalous Hall effect based memory system here. So now I will conclude this presentation by summarizing my contribution. So as I explained, we use this combination of ferroelectric speed and heat attraction device to design different components of the computing system. So we first developed a non-volatile memory systems, which are highly scalable compared to any other existing superconducting memories, and also they are compatible with the requirements of cryogenic environment. We also designed a voltage control logic circuit, which gives you higher fan out and better cascadability compared to the existing current control logic circuits. We also designed an in-memory matrix vector multiplication system where we only need attojoule of energy to perform 1 bit of matrix vector multiplication, and that can be useful for the implementation of machine learning and AI algorithms at cryogenic environment. We also designed this ternary content addressable memory where we have this modular behavior. We have 2 different modes, one for exact searching and another for the Hamming distance calculation. And we have this advantage for the exact searching mode where we get the binary decisions directly. And finally, we also use this heat attraction device to design a reconfigurable logic circuit, which gives us better area efficiency because we only used 1 device. And we also have better hardware security against reverse engineering attacks because of their reconfigurable nature. And we also use this quantum anomalous Hall effect phenomena observed in these topological devices to design, again, different components like the non-volatile memory. We have high scalability and ultra low power consumption during both read and write operations here. Then we also perform these Boolean logic operations inside this memory system where the key point was to be able to perform the XOR operation in single cycle inside the memory system. And then we also developed this in-memory majority system where we got this unique advantage coming from the QAC, because we could use the same memory systems to perform any input, majority operation with any input. And that also simplified the addition operation in the end. Now I'll talk about a few possible feature extensions. So as I explained, to achieve higher fan out in the current control logic circuit, we need to use this current splitter circuitry. And the reconfigurable logic circuit that we developed, that was current control, as I mentioned. So we'll also need this current splitter circuitry. And if you look into this current splitter circuitry, you see there are a bunch of buffers that creates this different number of output current with the same magnitude of the input current. But the buffers that we have, that you can see in the bottom of the left side, with the Josephson junction based technologies, they again use multiple Josephson junctions and multiple inductors. That's why the current splitter circuitry have like larger area and larger energy consumption. But the reconfigurable logic circuit that we designed, that can also be used as a buffer. and there we only have one device. So if we use this buffer to design this current splitter circuitry, that will improve the area efficiency and energy efficiency of the current splitter circuit significantly. The second thing we can also do is superconducting neuromorphic computing. As I explained in heater fraction, we have this integration of thermal phonons. If you remember, when you keep increasing the gate current, it keeps generating more and more thermal phonons, and they get integrated in the channel, and that actually increases the temperature of the channel. And after a certain threshold, it switches to the resistive state. So we have this inherent integration and firing capability inside this heater fraction device. And also, as you know, the heat transport is always a leaky mechanism. So we have this inherent leaky integration firing capability in this device. So we can use this device to design a leaky integrated fire neuron, and also ferroelectric squid can be designed used to design synapses, because in ferroelectric material we have this multi-domain behavior, which is used in room temperature to design analog type synapses, which can also be used in cryogenic environment with this ferroelectric squid. And together we will be able to develop a superconducting neuromorphic system. Finally, we can also use this heater fraction device for probabilistic computing. So when we got the experimental data from our collaborator from NIST, we observed that we have probabilistic switching nature in this device, which we didn't use in our reconfigurable logic circuit. So we designed our reconfigurable logic circuit in a way we kept some margins so that the circuit can handle those variations. But we can actually use this inherent variation and probabilistic nature to design a probabilistic bit, and we can develop probabilistic computing system. And again, because of this extreme energy efficiency of superconducting heater fraction, we will have better energy efficiency and better speed compared to any other probabilistic computing technology that we have. And again, to summarize, these are the lists of my publications so far. These are lead authored and co-authored journal papers. And then these are the list. This is the list of lead authored and co-authored conference paper. And recently, we also published a book on superconducting memory technologies, which is in Springer Nature, which is available online. And this is the timeline of my publications during my PhD. And finally, I'd like to thank AFRL, DOE, and Ethiopia Innovation Institute for funding my PhD research. And I'm also grateful to all my collaborators from different universities, national labs, and industries where their supports has been an integral part of my PhD research. I'm grateful to them. And that's all I had. Thank you so much for your patience hearing. If you have any questions, I'll be happy to discuss further.
Are there people in the room you need to thank for their support along the way?
Yeah. That's why I put the Utica logo like bigger than others. So
Everybody in here, just UT people?
here,
Yeah.
I also have my wife here. Yeah. Hard support is like,
If
I
you're
cannot,
getting a PhD,
yeah.
she's getting a PhD. Push hubby through.
Yes, obviously, yeah.
Yeah.
It's a 2-page acknowledgement.
Yeah.
He's a very grateful guy. That neuromorphic thing, can you go back to that? That was kind of, see, I think if I'm understanding right, it's there's a timing thing there that you're leveraging, right? So it spikes.
Mhm.
So if I get multiple really, really quick,
Yes,
then that's gonna, go into.
yeah.
It'll
Yeah.
switch,
And the
basically.
time difference between two spikes will be chosen carefully again,
Has
because
that been shown experimentally?
no, it's
Okay.
just
It's just theory.
We're writing
idea level.
proposals.
It's an idea level.
No,
Yeah.
so it's very cool.
So basically, trying to use the diffusive nature of heat. You
Yeah.
know, basically, if you keep providing spike and stop, it will
Right.
just diffuse away and not do anything. But if you keep doing it more, enough number of times, basically, this was all Shamiul's idea. We're just trying to leverage that.
And so for these materials, though, it's like enough if you say that is enough that you think you get effect like this.
Right.
Interesting.
Yeah, and there is a thermal reset time. So if
Right.
you apply all the spikes, you put the thermal reset time, so the
Right.
integration will happen. But
Gotcha.
if the thermal reset time occurs, then again you can start from the beginning. So you have that reset as well there.
Yeah, that thermal time constant's almost a fatigue thing.
Yeah.
That's what it kind of feels like. You gotta wait for that to settle, then it's ready. to go.
Yes. And if you wait for that thermal reset time, the device will switch back to the superconducting state, even if it's switched. So,
Hmm.
So for the Hall effect device, you didn't seem to have worked on it for the last couple of years. We didn't mention it in the future. What happened?
Yeah, we're,
Yeah, he didn't do it, right?
so the last work that we did was the majority applications, but we have other members in our group. We're also using my models to explore other applications with that. Like Mazhar here, he's also doing some sort of computing applications with that UAC phenomena. And we have like some other exciting applications, but the showstopper here is that, as I mentioned, that they are not that repeatable. Like, when you twist this two layer of graphene by a very small angle, 1.1 degree, there is some uncertainty that you will not get that degree. So when we show these large scale applications, that's not yet realizable now.
I mean,
Because-
how realistic is that nano amp current?
That's gonna be tough to do, right?
Yeah, that will, but the experimental data that we use, they actually supplied nanoamp level current there.
Right.
So they showed this current control switching of the Hall resistance.
The connection control.
Yes, that was experimental data, yeah.
I mean, there are source meters that can do that, but if you're trying to do that large scale and practical.
Yeah, right.
Yes.
Well, definitely. We
That's
have
why,
those as well.
again, just to add,
Yeah.
the selector type things can also be useful because there you apply the voltage and that gives you that current, nanoamp level. So you don't directly have to apply nanoamp level of current. You can apply a voltage, the selector, exponential selectors will actually convert that to the current that you need. Then you can have that in the memory element.
One of the thing is, non-technical note, the QAT quantum solid based works were taken over by some of his junior colleagues. He is trying not to step on their toes. So I kind of switched his direction towards more into regular superconducting devices. But in terms of timeline, when we portray this to our external conferences and places like that, we try to put superconducting stuff within 5 to 10 years in terms of realizability. And the topological devices beyond 10 to 15 in terms of DOE timeline, for example. Because of the challenges involved in. So the device that he showed, it was experimental developed by University of California, San Diego, sorry, UCSD. And then, they wrote a science paper. But then we understand that it's not really possible, given today's technology, to make a really big array full of these devices.
But that's a big group in MIT in physics. They are doing this twisted bilayer graphene. They are also doing twisted tri-layer, twisted tetra-layer. Even we saw some paper twisted penta-layer. So they are doing this. Dr. Pablo Herillo in MIT. So they are doing a lot of things, and they also showed that this same structure can also show superconductivity, like unconventional superconductivity, something like that. So yeah, they are doing a lot of things there.
There are multiple groups who have started looking at it. And one other thing that I forgot to mention, that his work was taken up by some of our system level collaborators, and they are writing multiple papers where he was a co-author.
Yeah.
So basically, it was not done directly by him. So
But they used my memory simulation framework for the memory system. They are taking that and they are modifying that to do some in-memory computing tasks.
any other questions from the audience first?
So if I do summaries of them. So we have parachute this memory and then parachute is some typical devices and we have quantum voltage and both of them will work in
Yes.
temperature and we compared it with memory stir which occurs at room temperature.
Yes.
We're kind of compared these two cryogenic temperature operating devices or memory-based devices with memory because of their features like non-flexibility, in-memory computing, and application. At this metrics that we are using to compare this.
Yeah. So, as I've explained, we didn't use energy efficiency or other metrics directly because they are they operate at room temperature and other memories at cryogenic temperature. But people have also used memory storage at cryogenic environment. So people have characterized memory stores up to 4 Kelvin temperature, and they are perfectly there. But we don't have any in-memory computing work with memory store at that 4 Kelvin. That's why we didn't compare in terms of energy consumption or other metrics. What we compared only in terms of accuracy to show from the high level that from the memory system, even if we forget about energy efficiency and other things, we get this type of advantage because of that memory design, which are our contribution. So the device, we didn't make them, but memory array that we have, we designed them. And we designed that in a way so that we get that separate read-write path capability. And that's what enables these advantages that I talked about compared to memristor. And
That's
yeah.
why we're comparing these two memory-based devices with memory.
Yeah, memristor is just an example. You can replace memristor with other memory technology as well. Like if you take ferroelectric memories or spin-tronic memories instead of memristor, the same thing will be there. So we'll have the same advantage there. So we are more familiar with memristor because we have worked on that as well. That's why we use memristor to compare that. But instead of memristor, you can use other memory technologies as well. Yeah.
Understand.
Yeah, sure.
And one other thing is when he wrote the paper, it was probably, I mean, arguably, we could claim that the very first paper about cryogenic in-memory computing. So it gets a lot of citation because other people write papers now. So he didn't really have any other data to compare against that showed cryogenic in-memory computing. So he had to live with room temperature and other comparison. But now there are many other papers. So I guess in future we can do more comparison. Any other questions from the audience? Someone from the Zoom, I don't know whether anyone from Zoom has any question.
We have Maria and Jack.
If not, then I would like to request the audience to leave the room and
Zoom.
yes, including Zoom. Maybe we could
Stop
basically just stop or maybe just end the Zoom
Yeah.
session because we don't need it anymore.